Well, hopefully you may have noticed that there were a few relationships that we've already been using in terms of these right triangles for our trigonometric functions that were, well, interesting. They were useful, right? For instance, we have what we could consider an inverse identity. Oh, you recall that when we talked about the sine of 30 degrees, right, we found that the sine of our 30 degrees would have been equal to 1/2, and that the cosecant of 30 degrees was equal to 2. These two are inverses of one another. We just simply take the reciprocal. I say inverse identities. I guess I should really say reciprocal identities. Let's call them reciprocal. These reciprocal identities apply for each of the trigonometric functions. So, for example, sine of theta is equivalent to saying 1 over the cosecant of theta. Or likewise, cosecant of theta is the equivalent of 1 over the sine of theta. Cosine of theta is 1 over the secant of theta. It's the reciprocal. So secant and cosine are reciprocals of one another. And finally, tangent and cotangent are also reciprocals of one another. So our reciprocal identities are these ones. We also have a couple of ones that are called ratio identities. And these ratio identities, we actually can find that the tangent of an angle is equal to the sine over the cosine of that same angle. I'll give you another example when we talked about our sine of 45 degrees. Well, the sine of 45 degrees was equal to the square root of 2 over 2. And the cosine of 45 degrees was also the radical of 2 over 2. Well, what happens when we divide them? Tangent of 45 degrees is equal to the sine over the cosine of 45 degrees by this ratio identity. And so if we take square root of 2 over square root of 2 and divide it by itself, we get 1. And that is the tangent of 45 degrees. We have 3 Pythagorean identities. Now, this is sort of an interesting one to prove, but if you were to take our right triangles and work them out, we're going to find that if you take the square of the sine of an angle plus the cosine of that angle and you square it, you're going to get 1. Right? So how would we prove that? Well, let's just take a moment and think about having a right triangle with sides A, B, and C. And if we have our angle theta in here, what could we say? Well, a squared plus b squared is equal to c squared. Well, what happens if I divided everything by c squared? Well, what happens is we get the ratio a over c squared, and the ratio b over c squared, and that would be equal to 1. Well, what is a over c? A over c is adjacent over hypotenuse, cosine. B over c is opposite over hypotenuse, sine. So when we square those ratios, that is, we take the square of the sine plus the square of the cosine, we get 1. Well, it's also provable that we could get 1 plus the square of tangent is equal to the square of the secant of that ratio. And if we were to take the square of cotangent of an angle, add 1, it would be the same as taking the square of the cosecant of the angle theta and 1. All right, one last set of identities that we might want to know called the cofunction identities. Here's the way these ones work. We actually mentioned it before. We had said that when we take the sine of 30 degrees, we would get 1/2, and the cosine of 60 degrees would also give us 1/2. When we were looking at our special triangles, so sine of 30 degrees and cosine of 60 degrees are the sine and cosine of complements. It turns out that if we take the sine of 90 degrees minus 60 degrees, which is 30 degrees, You get exactly the same values if you take the cosine of 60 degrees. The two angles are cofunctions. So sine is a cofunction with cosine. By the way, pi over 2 minus theta also gives us a complement for theta. Tangent, 90 minus theta, is equal to cotangent of theta. Tangent and cotangent are cofunctions. Secant of 90 minus theta is equal to the cosecant of theta. Secant and cosecant are cofunctions as well.